is what we did in 2012. As far as we're aware, this was the first work on this kind of large web-scale web service with real data, with real outliers, that uses anomaly detection and tries to predict failures. So the idea was basically, again, we talked to this Bob, not his real name, and we wanted to break, he said, like a cycle of frustration. So we said, okay, first of all, we're going on limit false positive. We don't want you to have this. It was very important for us. We say we want to predict your failures, or at least detect these anomalies before you get a call of VA, hopefully. And what we did basically is this kind of new anomaly detection algorithm that when you compare it to real data, turns out it can predict some failures, not all of them, up to between 7 and 14 days in advance. We also have real evidence from a real system to show that if you look at machine failures from whatever monitoring you're doing now, or at least they were doing then, which was basically manually set threshold and tuning manually, turns out that these latent faults, these anomaly detections, subtle anomalies, precede at least 20% of real failures. So it doesn't, for some people, sound a lot. What, 20% failures? First of all, if I tell the support engineers that we detect a week in advance 20% of their failures, they will be very happy. It means they have a lot more time to deal with fires that break out, like real emergencies. If I convert 20% of their emergencies to non-emergencies, they're super happy. Also, this was, and you will see, a conservative estimate. It's probably not 20%, probably more like 40 or 50. One thing we wanted to do as a system, and you'll see why, it should be easy to use. You do not need any labeled examples. You do not need to do any modeling. You do not need to tell the system what kind of system are you monitoring within some very specific assumptions. You don't have to tune parameters. And you really want it to be practical. You don't want it to intrude in the application. You don't want to change stuff in the application. You just want to use them, whatever they collect, and just give us your logs, your logs, and we will give you some output. That's what we want to do. So how could this work? So let's say I have C metrics that I'm measuring, measurements or counters or performance counters, call it whatever you want. Like I said, CPU time, I.O., stuff like this. Let's say I have C measurements and I have M machines. And again, this was targeted at web servers, so we assume that M is very big, and these machines have a load balancer, so they are roughly doing the same work. So it kind of looks like this. This is machine 1. We collect data from T times, let's say every 5 minutes during the day, so T is 288. Okay? If I collect every 5 minutes for an hour, T is 12. C is the measurement. Like I said, each one of these is some sort of performance counter or metric. And of course, I have M of these. And one of them, or more than one, is an outlier. Something is subtly wrong. I don't know what, but maybe too high, too low, not right. Something is incorrect. And we want to find these issues. So what we're going to do is exploit homogeneity assumptions. So what do I mean by that? First of all, if you look at a large web service for a real physical machine, they don't just take machines from anyone. They buy machines from logistical reasons. They only have a few hardware configurations. These are all the same. Maybe they're not. Maybe they have 3 or 4 different configurations, but they have so many machines. So for each subgroup, for each configuration, you can still find thousands of machines that are identical. And they also run the same software because it's a large scale-out web service. They also have homogeneous workload, not during the day because you can't predict that. But on average, on every point of time, machine 1 gets pretty much the same workload as machine 2. Maybe if it gets a little bit too much now, next time it will get a little less. Because it should be, this is what load balancers are supposed to do. They're not perfect, but on average during the day they're fine. And also we assume that most machines are okay. They don't have a latent fault. Most machines should be fine, otherwise the service is not working at all. So let's say 90% of the machines are fine, which makes sense. So what we think is that those healthy machines, machines that are okay, exhibit similar behavior, and faulty machines are consistently bad. And I'll show you what I mean. Let's say M is a healthy machine, and I look at all the other machines in the cluster, in the server farm. And I just measure at each point of time all the metrics. Okay, like I said, I have C metrics, I just measure them, it's a big vector. Let's look at the average direction. These are vectors, I can compute the difference. Okay, so at time t0, this is the machine and these are the others, so the average direction is kind of like this. And at time t1, maybe kind of like this, and t2 kind of like that. Basically, it is random because of the load balancer, because the machines are pretty much the same. Every difference between this machine and all its friends is mostly random because it's just noise. They are the same hardware, they run the same software, and they have the same load on average. So basically all these differences tend to be random. And when you add up random vectors, you get a short vector. Because up, down, left, right, it's 0, right? If you just sum this up. So, but what if a machine has a problem? Let's say it has a slow hardware. Why is it slow? It's about to fail. It means that maybe all I operations are a little slow, so latency is a little high, you can't write as much. This is a consistent failure. When you compare this machine to the other normal machines, it's always the same issue. So when you look at the direction of the vector, it's always kind of pointing to a similar direction. Not in all dimensions, but some of them. So what happens when you add these vectors together? You get a long vector. So this is the sign test. This is one of the things we come up with. You take the average direction at each time. You average this average direction across the day. You compute using some concentration inequalities. You can actually put some statistics to limit false positives there. And you compute what does it mean if the vector is too long from all the others. And if it is, if the probability is low, below, let's say 1%, we say, oh, this machine is an outlier. I'm going to skip this. And using a similar idea, the idea of averaging across between the machines at each point of time and averaging across the day, you can also have some other tests based on other ideas, not just direction, there are other ideas. And where does this work? Well, I'll show you it works in a minute, for now you trust me. But one of the nice things about it is that we don't assume, beyond the three assumptions, we don't assume too much about what these machines are doing. And if the workload at time t1 was big, and workload at time t0 was small, it doesn't matter, because I compare the data from t0 only between these machines, and at t1 only between t1. So I never mix different times, which means that even if, like 5 minutes ago, no one knew anything, and now there's an earthquake, so everyone is searching for earthquakes, and the workload is very big, I never compare workloads between different times. So whatever and even if you update the system, let's say you push new software now. So 5 minutes ago, the software behaved in some way. And now it behaves in a different way. So of course, all these performance counters might behave very differently. Maybe you did some optimization. But it doesn't matter because you updated everything. Or at least we hope so. So you don't have to retune the system. It always compares apples to apples, oranges to oranges, never between each other. Always a time t0 between everything, time t1 between everything. So this is why it works. This is why you don't have to tune it. This is why you don't have to tell it what you're doing. You don't have to tune parameters. You don't have to change. When the workload changes, you don't have to do anything. And we have some empirical evidence, which I will show you now. Basically, like I said, we took a very large web service, search index. We took a small part of it, around 4,500 machines, and we basically looked at what happens to them. We ran a test with historical data. We looked what happens to them for 60 days. And it's a big data set, we had to do some fancy parallel processing. And we validated using historical logs. Whatever health logs they had, we used that to validate our results. I just want to remind you, outlier is not the same as a machine failure. Let's say on day 1, machine 5 is an outlier. How do I know I'm right? So we looked at this machine for the next, let's say, 1 or 7 or 14 days and see what happens to it. If it fails, then I was right, we have a true positive. If it didn't fail, it was a false positive. And if I said the machine is fine, and it fails 2 days later, then we have a false negative. I said it was fine, but it was not fine. And so on and so forth. So just remember, just because something is an outlier doesn't mean it's really interesting. This is why it's very important. So here's how results might look. This is again time, some value of some metrics. These are 4 different metrics. Basically, when we look at the output, it might say, oh, each gray line, there are multiple gray lines, and you don't see it, it looks like a big thick line. But there are multiple gray lines in these figures. Each one belongs to a different machine across the day. The one single black line is the machine that we think is faulty, that we think is an outlier. And you can look and see that, oh, this machine, whatever this is, maybe memory, it's using more memory than everyone else. Everyone else is using this amount of memory, and this machine is using a big amount of memory. And the same here, this is, these machines kind of behave the same. There's this wave pattern here, and this one is way higher, it doesn't see the wave pattern. Here is whatever it is, it's too high. I don't even remember what this one was. So this is basically the sort of output that we would get. You will see, oh, this machine is faulty. We also output something to help you try to figure out what the fault is, but I'm not going to get into it now. And you get some sort of probability that say, oh, this is faulty. I think there is a 10 to the power of minus 23 chance that it is normal. And I really think it's really bad. You get a p-value for those who know hypothesis testing. So, okay. First of all, how do we know that outliers are important? How do we know latent faults are really latent faults and not just some outliers? So here's what we did. We chose machines that we knew were failing. And we chose machines that we strongly believed that they were healthy. You can never say a machine is okay, maybe it's not and you don't know. But we looked at machines that didn't suffer any problem for like, I think 160 days, like absolutely no problem. And we also took some machines that suffer like a known problem. And then we said, okay, this machine suffered some problem at some specific time. Let's go 1 day before that, run our statistical test, our outlier detection, and see what happens. So the result was that at least 20% of failures, I could have predicted them maybe a day in advance. This is really nice. Like predicting failures, at least 20% of real, actual failures that we tested. And we were very precise in this specific data set. We had basically 100% precision. We were never wrong. We had 0 false positives. Every time we said the machine is about to fail, it was failing. For those machines that didn't fail, we never even indicated one as failing. So for this small data set, it was good. And this 20% is actually an underestimate. If you know the civil operator characteristics, it's good. If not, we'll skip it. But we could have settled, if we were willing to tolerate, about 20% false positives, which some people are, because usually you might just reboot the machine. So sometimes you could say, if you have a false positive, it's not so bad. We think it's bad. But if we were willing to tolerate more, it could be 40%. Okay. Let's look at a real web service for 60 days and see what happens to it. Now, in this service, every day, you either get 2% of the machines, which remember there are quite a lot of, experience some sort of failure. It doesn't have to be a hardware failure. Usually it's actually some software failure. Some process crashed or the machine was rebooted. It's not always it's not always some hardware going bad. But still, 2% failures every day. So we want to see if we can predict failures up to 14 days in advance. So here's a figure. I'm just want you to concentrate on the lowest graph. Basically, it means I tested the machine at time 0. What happened to a machine 1 day later, 2 days later, 3, and so on, up to 15 days later? Now, the lowest figure shows how many machines failed out of the total. If I just choose some random machine, after 15 days, 20% of them will fail. Okay? But this is basically a result of this 2% failures per day, but it's actually based on real data. So this is actually made from real data. And let's say I apply one of our outlier detection tests. The best one is one right here. And again, out of those machines that I tell you I think will fail, how many failed in the next 14 days? So let's say, in the next 7 days. In the next 7 days, around 55% will fail. If you are saying, oh no, I care about 2 weeks in advance, around 70% will fail. This means, who know this, it's 70% decision, basically. If you predict 40 days in advance and you tell your machine is failing, there's a 70% chance that it will actually fail in the next 15 days. Which is very nice, because if you just go for a random machine, it would only be 20%. So this gap between the top and the bottom, this is where we're strong. It doesn't show here, but in terms of false positive rate, we have a statistical hypothesis test, which means we can actually set a limit on the false positive rate directly. We set the limit to 1%. It will turn out to be 2 or 3. There are reasons for that I'm not going to get into, but still 2 or 3% false positive rate is very good, especially if you have 70% precision, and especially if most machines do not fail. And we even found previously unknown failures in a real service. One of them, we found a failure. The monitoring system didn't say anything about this machine. Turns out the database was completely corrupted. This machine was running. They thought it was okay. It was not. Whatever request you sent to that machine, it would just ignore it because it cannot do it. The database was just not running. They had a machine running that was not doing nothing. I don't know how it affected the service. Maybe some people ran a query and didn't get the results that they wanted. They had to wait. I don't know. We have found 2 machines with a bad network card. So each machine, because it's redundant, each machine has 2 network connections. But we found 2 machines that have a really huge amount of errors on one of them. So of course, this is built for redundancy. So it switched to the other network card. But it means that they didn't know, like in theory, you switch to the spare network card and you replace it. But they didn't monitor the situation. So if they had another failure, these machines would be down. Which brings us to a nice point where if you're doing backups or having hot backups or having some sort of backup in your system of any component, if you're not looking at what's going on, it's not going to help you too much. And I mentioned the idea that it's flexible. So if you look at the 60 days that we test this machine, you simply plot the precision. Okay, and like I said, it's between 60 and 80%, except for what are these weird gaps? Why is our precision dropping from an average of 70% to 40%? What happened? We didn't know. So we then went back to the logs of the system. Turns out, what they had there was rolling updates. They basically took some of the systems off, replaced the software, but not all of them. So we thought these were outliers, but they were not. But look at this. After the service update after the service update finishes, which takes about 2 days, the performance came back. So they updated the entire software, and we didn't have to do anything to get the performance back for our outlier detector. So that means it really is flexible like we wanted. Turns out one of the systems that we tested, they completely changed the architecture of the entire system, the way servers talk to each other, the primary servers and secondary machines, so on. They completely changed everything, and you still didn't know about it, just walked. Except we basically see these spikes and then it goes back up. Also, there was a, we know there is a weekly workload variation in the service. There is a cycle there, and we don't see it. The performance is pretty much the same for the entire week, for example here, which means that when I mentioned that we can adjust to different workload conditions, it turns out to be right on this. So we're quite happy with it. We were quite happy with this, and except one thing. The problem was that I mentioned before, we needed a big, massive parallel processing framework to process this data because it's so big. It needs a lot of bandwidth to send it to all these. If you think about it, you collect 5 metrics. So you collect something like 200 or 300 metrics for each machine every 5 minutes for 4,500 machines. And then you do it again for all of them every 5 minutes for the entire day, all the time. It's a lot of data to send around. And it is a lot of data to process in one location. So we're not quite happy about the scalability of our solution. It kind of worked, except on a cluster, it took about 2 to 3 hours on a cluster of few tens machines to process the results from all of these, which is bad for us. We want to be faster and also more bandwidth efficient. So our goal was to take what we did before and reduce the data size and communication by 90%, and we wanted to have an online algorithm to reduce the need for some of the computation, and we didn't want to introduce a lot of additional errors because we were quite happy with the precision of the algorithm, so we didn't want to ruin it. I am not going to explain how we did this. Those who were yesterday saw some of it. We don't have too much time. I'm just going to briefly describe how we did this. Those who understand, good. Those not are welcome to ask me later. So the first scaling problem is data size. As I mentioned, too much to centralize. We send C measurement every sample. So the first thing we did was something called sketching, which is the idea that you apply some sort of, in this case, a random projection to the data. You apply, you started with C, maybe 200 metrics, and you reduce it to K, maybe 10. So already you saved 95% of the data. And it turns out, if you do this kind of sketching, you can still do the sign test, as I explained, compute the differences between vectors and correctly, even though you're using a much smaller vector. So, again, I'm not going to explain. You're welcome to come and get the details. Second problem we had is the idea that we want to process it on some machine. So, previously it was you need to do O, T, M square C operations. Now it's O, T, M square K. Because C was 200, now it's K, it's 10, much better. Still not good enough. So we did an online variation of the algorithm where we incrementally update all the probability values and incrementally update the differences with a sliding window. It's actually not very complicated. I can give you the details if you want. But basically, you reduce the memory cost to O, K, M, T, and each incremental update is O, K, M squared. So for a good portion, when we did this for a smaller subset of the data, we could easily do it on one laptop in seconds. So which means basically, instead of having 20 machines do it, you can now do it in one. So very good. And the last problem is, I'm just not going to get into it. We had to do some pre-processing on the data, which requires each machine, before it applies a sketch, has to normalize the data to unit variance. Each of the metrics that you collect, you have to normalize. to unit variance. But to know the variance on machine I, it has to know the variance for the entire metric across all machines. So you'd have to send the data to compute the variance. So we have some communication efficient normalization using a communication efficient variance estimator. Those who were in the course yesterday, I explained it. Those who can, just not have too much time. I'm just going to get into the results quickly. Turns out that you can reduce communication by 13%, to 13%, and you don't get any classification error at all. That is very nice. And you can, if you are willing to tolerate 1% classification error in addition to whatever previously had, just an next, like 1% error, you can really reduce the communication to, well, basically 10%, which is what we wanted to achieve. So again, we were quite happy with it. This was tested on similar data from before, but smaller subset. Okay. I talked about web services. What about other things? What if you have unbalanced workload? You don't have a load balancer. Maybe your cloud workload is still running in cloud from web service somewhere, but the load balancing is now statically done by perhaps the user ID. So each user always gets the same machine. So some machines may be getting very heavy users, others not. The load balance is light load. What if you're using Hadoop or some sort of parallel computation where they try to do load balancing but they never succeed? Or a supercomputer where the load is distributed by humans rather than a load balancer. So if you revisit our assumptions, we still believe that you have homogeneous machines. We still think the majority of machines are okay. But this is no longer good. There's no longer load balancing, which means if you compare the metrics of machine A to machine B, then you are not going to work. It's not just not going to work. Because if one machine has always a busier workload than machine B, then it will always be detected as an outlier, even though it's not. It's just getting more jobs, more work. So how are we going to deal with that? Basically, instead of looking at the raw metrics in the sign test that we've previously seen, we are going to look at the relationships or correlations between different metrics. And we're going to assume that, a machine is doing some sort of work, right? It's running some code. And we are going to believe that there is some inherent correlations between metrics, and these depend on the code that the machine is running rather than anything else. And even if you give it a higher workload, these inherent dependencies are still the same, because they depend on the code, not on the workload. So we will identify this relationship. And I'll show you how it looks. Let's imagine a hypothetical, very simple server that for each client request needs 10 megabytes of memory, 3 database transactions, and 2% CPU, which are the things that we are measuring. Okay? Let's imagine. So here's an example of 3 machines that I measured for the last 5 minutes. This one week had 3 requests. This is the amount of memory, database, CPU, and so on. So we can establish a rule, right? This is the rule. Memory divided by 10 plus this and so on. Basically, it's the rule I just described previously, plus this 60 because the memory starts at 600 megabytes because, let's say, the OS has more. It's actually, usually today it's much bigger, but still. So this is the rule that we have. And we think if there is a problem in the machine, a latent fault, it will deviate from the rule. It will cause some deviation from the established rule. Maybe there are database errors. You need more or less database transactions. Maybe you have a memory leak. So the memory is higher than what you would expect given the CPU usage. Maybe the CPU usage is too low actually for something, or too high, and because of garbage collection or whatever. And it's too high and you don't expect it. For 3 database transactions, you need this much CPU. So if you look at this table here, It's hard to see, but this machine is an outlier. It only has 3 requests, but the memory is 740 megabytes, and it should be around 630 maybe, or 650. The database projection is still the same. The CPU is also a bit higher. So this is an outlier because this rule is not valid for this machine. This rule that we've established. Now, if we just do the right plot, you will easily see it with your eyes, right? If I just plot the number of requests in the CPU, you can easily see this machine here while all the others are here. And in fact, you can also see something else. For this case, these are all on a straight line. This machine has a high load, this machine has a low load, but they are all on this straight line, while this machine is not. This is the basis of how we will do it. So, again, it's similar strategy to what we had before. At every point of time, you establish these rules, given the majority, like you have most of the machines, so most of them are fine. So if you establish the rules correctly, you establish the right rules that are fitting for the most of the machines. So at every point of time, you establish the new rules, you check if the machine is an outlier. Then you move to the next point of time. You establish again the new rules, you check if the machine is an outlier, and you keep doing that. If a machine is an outlier all the time, as before, if a machine is consistently an outlier, it means that there's probably something very wrong with it. Or it may be a little wrong. And again, use some statistical properties to limit false positive, either Jackson and Manholker value, if you know it, or some modern idea, or basically the same idea that we developed in our previous work, which turned out to work very well. So, for those who know, PCA subspace decomposition. Many people have heard of PCA, so I assume most of you have heard of it at least. And the idea is this. What we're going to do is say that the metrics of the machines are composed of, let's say, a normal behavior subspace and the abnormal subspace. So some of the metrics come, or a mixture of the metrics come from the normal behavior, which is the line, the straight line that I will quickly show you, and the abnormal subspace. This is done using PCA, or principal component analysis. The principal component, for those who are familiar, form the normal subspace, and there are a few, and most of the other components form the abnormal subspace. Hopefully I'll show you a look. And we simply project the data to the abnormal subspace. Good points, good machines, come from the normal subspace. So when you project them to the abnormal subspace, they have little presence. There are small vectors. When you project points from a bad machine to the abnormal subspace, they are an outlier. And we use some random modern version of PCA to deal with outliers, because we know the data has some bad machines. So this is kind of how it looks in 2 dimensions. This is the normal subspace. If you project these machines, and this is of course the perpendicular abnormal subspace. So if you project the blue machines on the red line, you get a small projection. And if you project the outlier on the red line, remember the red line is the abnormal subspace, you get a big projection. So this is kind of similar to what we had in science. Hello? Okay. This is kind of similar to what we had in science. Big vector, bad, good vector, big bad machine has a big vector, good machine has a small vector. Again, using this pretty much the same ideas, the same assumptions, only we now somehow deal with workload, statically different workloads. And why does that work? Because, again, the normal subspace is a line. If you have a high load, let's say these machines have between 30 and 40 requests, so they have more CPU, so they are here. These machines have between 0 and 10 requests, so they have low load, they have low CPU, but they are still all lying around the normal subspace, rather than the abnormal. And as before, because we recompute this PCA, this projection, every point in time, then it means that we are robust to changes in the system. Because if you change it, then 5 minutes later we will recompute the rules anyway. So whatever changes you make in your system, we will find them. We will find the new rules anyway. So how the algorithm really work? You just take the n by c matrix for each point in time, n machines, c measurement. This is what you get for each point in time. You do a PCA, you have to standardize the data. If these are the principal components, then the abnormal spaces are computed like this. You project to abnormal subspace like this. I'm not going to belabor the point. We use the statistical framework that we had from the previous paper to limit false positives. We have a p-value, same idea as before. We integrate across time. Okay. Now what? So this was actually work from preliminary work. We have some preliminary results. So we took a supercomputer log, logs from Tsubame 2. We took 1 month of job. We had a lot of problems there. We had no idea what machine was running, what machine was not running. We just had the metrics. So these results are not perfect at all. But we compared that we did have their failure log. So we could compare, when we say an outlier is an outlier, we can compare whether it's failure or not in the next 7 days. So first of all, we looked at our original latent fault detector, the one that I explained previously, the sign test, the 2 others that I said worked very well on a large web service with load balancing. But a supercomputer does not have load balancing. So those of you again who read the receiver operator characteristic or ROC curve, basically what you see here is that it's no better than flipping a coin. Our previous test was no better on this use case with unbalanced workload than flipping a coin. So the new variant is a little bit better, not a lot better. It still has it doesn't issue alerts if you want to be correct. It's not great. So we kind of just did something else. We went to a company that does basically has some sort of hosting with virtual machines, does a private cloud, and we said, okay, let's try Cassandra with virtual machines rather than physical machines and rather than a supercomputer. And this time, we control the environment so we know which machines are running what, so we're not getting this problem that we previously had. And we injected some failures. We basically injected disk failures or disk hogs or CPU hogs and memory hogs. Basically injected failures. And what we can see is basically it works really well. It's not, again, those who know what curves can see the more you are near this point, which means 0 false positives and rate 0 false positive rate and 2 positive rate of 1. It's this point. So the green line over there, this is what we can do. We are very, very near the best that's possible. This works similarly with Hadoop. The previous test did not work well at all. Like the dotted line is a random, just flipping a random coin. If you're above it, if you're just a little above it, like this purple sign test that previously worked so well, you are barely getting any results. This is not so great. And so on. So again, these are preliminary results, but this looks very promising. So if I had an Hadoop system, I would probably try this, definitely rather than the previous test. And I'm going to skip, we had some other specifically tailored for virtual machines based on sparse decomposition. Again, it's still the idea of outlier detection. You detect an outlier every point in time. You see if it is consistent, and if it is consistent, you say this machine is abnormal, and then you really need to check if it's abnormal or not. So I'm going to skip this because I want to mention some other things to conclude. So, kind of, if you look at the evolution of how you do health monitoring in the data center. So, the classic method means, again, manual thresholds, manual rules, adjust them every time you have some problem, every time you change the system. system, you really hope that the same old rules apply. You're probably missing a lot of important alerts. Despite this, this works, and people still use it. It's not great, but for me it means that as people who were dealing with this kind of thing, not offering good solutions, basically. If they're still using this old method of manually adjusting everything, it means I didn't give them a good enough solution. That's what it means. There was some brief flirt, let's say, with supervised learning, and I talked to some of the people who did this work, and at least some of them, it looks like they're not happy with supervised learning for this problem. If I were you today, I would probably try, and I'm sure someone is doing it, but probably at Google, using deep neural networks for this problem. It's still, and maybe this would work this time. Okay, maybe. But it's not great. It has not been great experience. Basically, our results tend to either surpass or work at best with the best in breed supervised approaches. Our outside detection approach is much more flexible. So even if you take the best in breed supervised approaches and you do all the learning, all the training, all the filtering, all the labeling, you're not doing any better than what we're doing in outside detection so far. That I've seen. Okay, so, and then you look and you see, I think the last 2 or 3 years, more like 2, that the big companies are really starting to do this outside detection thing. In Israel, there are several new startups that say we will do outside detection for the data center, will find problems, and so on and so forth. And okay, are we done? Okay, outside detection is the solution, right? So of course not. If you talk to your ops team, or depending on sometimes DevOps, sometimes called something else, you talk to your ops team. What do these guys want to know? First of all, they want to know the system, the entire service as a whole is running well or not. For this, there are solutions. So people do this. They know how to build a dashboard. They know how to know this. They do want to know which machine is failing and which machine is about to fail. So this is something we can give them with the outside detection. It works. It's not perfect, but it's better than nothing. But they also wanted to know why it's failing. It's not enough to give them, they have 1,000 machines. If I give them a list of 20 machines every day that says, I think these machines are about to fail. I think they will be happy with that. But what they will really be happy is that when they answer why, I can give them some answer. So there is a lot of work on this, including for us, to give this answer. Maybe you see which of these metrics that you collected are the actual outliers. Maybe you want a different, maybe you do some, after you know a machine is about to fail, then it's easier to do the labeling, and then you can do supervised machine learning, because you don't have to do it for all the million machines that are not failing, but only for those cases where they really fail. Then you can do some supervised machine learning, because it's much more easier to do the labeling. Much less data to work on. There are the issues of basically root cause analysis. What caused this failure? Not exactly why you think this machine is about to fail, or it has a high memory usage, but why does it have high memory usage? Again, why all the time? That's what ops team want to know. Linked failures. Just because if machine A is failing, they can bring down also machine B, because machine A is the server that machine B needs to know to get this information, and machine C is depending on machine A. So you get all these cascading failures. Which is the root cause? And how should you ignore machines A and B, because what's really important is machine C that's failing, or should you say, no, we should collect all of them? Could you even, like, if too many machines are dependent on each other, could you even notice that there is a failure if you're doing outside detection? We don't. And still, it's very, very important for the ops team, you want to limit false positives. There are various ways to do it. We really applied some rigid statistics to say, oh, we want to limit false positives to 1%, period. Or you could say, you know what, I'm not really sure, but I'm willing to give you every day, I will look at the 10 machines which are the top outliers, the most outlier machines that I can see, and you get 10 every day. And you say, oh, I have enough people to handle 10 machines every day, so why not? Well, that's one way to do it. Another, like I said, is robust statistics. And the point is that this is hard. And no, so unsupervised machine learning is not, like, outlier detection is not the only thing that you should be doing. Should be doing supervised learning as well, maybe for a different subset of the problem, maybe somehow combine them. This, again, some of the new approaches that I've seen in KDB and places like this is what they're doing. They're mixing outlier detection on one level and a supervised machine learning approach on another level to arrive at some very nice results. This is hard, so you use whatever you have. And I've seen approaches from like graph theory and dependency graphs and dependency analysis to deal with link failures and root cause analysis. And there's a lot of systems problems. I see systems research that don't actually detect the outlier, but if you do know the outlier, you can find out what was wrong and where in the code. So don't limit yourself to just saying, I started and I thought, oh, this supervised machine learning will never work. And the people who started with supervised machine learning, they said, no, we have to do supervised, it will work much better than outlier detection. And in the end, we kind of each have seen that we are kind of drifting to the direction of the other one, somewhere in the middle. We have to use everything we have. So if you're doing it, do everything you can. But it's important also, what I've learned is to keep in mind, work on real systems. Try to work on real data, otherwise, and I've seen a lot of work that kind of works in the lab, but it would never work because I've worked always with real systems data. It would never work there. Like I said, just label everything. But if you talk to the ops team, they will never label everything. It's not practical. So a lot of these, so you have to keep in mind, you have to keep in touch, you have to talk to the ops team and see what they say, what they want, how they work. Otherwise, you're just like, okay, maybe you get a paper out of it. Maybe not. If I'm your reviewer, you will not get a paper out of it. Thank you very much for listening. And if there's time for questions, if not, I'm sure